So I'm just hitting go live, so I'll remove myself in about 10 seconds. And then we'll be good to go.
Should I start sharing the screen now or?
Yep.
Okay. Okay. Can I start?
So maybe I can introduce you. So thanks. Welcome to this second session of QPL. So we have the pleasure to welcome Sebastian Horvat, who will talk to you about interference as an information-theoretic game.
Can I start now?
Yes.
Okay. Yeah, thanks. So yeah, hi. My name is Sebastian, and nice to meet you. And I will talk about work that I did with my supervisor, Borivoj Dakic. And yeah, the title, as you heard, is Interference as an Information-Theoretic Game. And I will immediately start by a brief reminder of the double-slit experiment, just a standard textbook thing. So we have a plate pierced with two slits, which can be either open or closed. And here I will indicate whether they are open or closed by a number, which can be just 0 or 1, just a bit. So 0 will indicate that the slit is closed. 1 will indicate that it's open. And the experiment just consists of sending a particle through the slits, and then the particle hits the screen at some point. And we introduce the second order interference term in this way as a combination of these probabilities, where, for instance, this one, P10, is the probability of detecting the particle at some point of the screen, given that the states are in states 1, 0, which just means that x1 is open, 1, and x2 is equal to 0, so it means that it's closed. And we know that in classical mechanics we get I2 equals 0 because the particle has always a defined trajectory, it always goes either through here or through here, while in quantum theory we get some interference pattern and I2 can be non-zero if the particle is in a superposition. Then next, Sorkin introduced multi-slit experiments as straightforward generalizations of the double slit by just adding more slits. And the experiment is still the same, but now we have a new interesting quantity, the third order interference term, which is again a combination of probabilities, where this P x1, x2, x3 is the probability of detecting the particle at some specific point on the screen, given that the slits are in states x1, x2, x3. So for instance, 1, 1, 1 would be there, they're all open, and so on. And it turns out that in quantum mechanics, I3 is equal to 0, which makes us question whether we could come up with some counterfactual theories which would exhibit I3 different than 0. And then the natural question to ask is why second order? What is so special about 2? Why not 3 or 4 or more? So yeah, in the same words, what are the physical principles forbidding higher order interference? And this consequently led to a definition of higher order interference theories within the GPT formalism in terms of states, effects, transformations. And there has been a result where the authors derived the result that purification and sharpness and some other principles imply necessarily second order interference. However, here I will not talk about this in this direction. So how to physically understand, so how to physically single out second order interference, but to try to maybe reformulate the whole question and to try to redirect the question to something different. So instead of dealing with interference experiments, we will be dealing with certain games. And so one way to introduce these games would be to just notice that the standard interference experiments, just in the double and multi-slit experiments, are defined explicitly for single particles or single systems. that the slits are either open or closed. So it's either one or the other possibility. There is nothing in between or more possibilities. And the final measurement is implemented by a screen, just detecting the particle or not detecting the particle. So one way to introduce these games would be the question about how to relax the aforementioned restrictions. And so now a proposal would be to treat interference experiments as a game and to try to extend these experiments in terms of a game. So this is a simple example with just two slits. It looks very similar to the picture before. Now here we have Alice, who sends a particle through the slits. The particle arrives to Bob. He gets the particle, reads the particle, or makes a measurement, and outputs a bit B. And the rule of the game is as follows. So in each run of the game, in each iteration of the game, Alice prepares the slits in state x1, x2, and Bob doesn't know which of the four combinations the slits are in, and sends her particle towards Bob. And in order to win the game, Bob must output the parity, which means just x1 plus x2 modulo 2. So it's just an XOR game. And then the quantity of interest is now this thing, which it's I2 but with a tilde. It's very similar to the thing before, but a little bit different. So this is the average probability of Bob winning the game. So of the probability of Bob outputting x1 plus x2 modulo 2, given the inputs, and average overall inputs. And minus 1/2, this is just the random guess probability of winning the game. And this thing is very similar to the expression that we had before. If you constrain Bob to making measurements with a screen. But now in this game, he can do whatever he wants. But now we can easily generalize this situation, this game, to just sending more particles or systems. We can just say Alice can send whatever she wants. And the bits are implemented by arbitrary local operations. They're not anymore just slits, which are either open or closed, but can be some boxes which implement the local operations. And Bob tries to retrieve the parity, tries to decode just x1 plus x2 modulo 2 via any operation or measurement, in any way he knows, not necessarily just with a screen. And then in this way, we get this picture, which just says that Alice now sends something, some particles or systems through two boxes, which implement local operations depending on their bits and on the input bits. And the particles then arrive to Bob, and he does something and tries to retrieve the parity. And then we can also define a higher order game, which would then be a generalization of the multi-slit experiment, where now we have just more boxes. Now, in this case, the figure of merit is the mth order, like the redefined mth order interference term, let's say, which would be, again, the average probability of Bob outputting the overall sum modulo 2 of all the inputs. And again, minus the random guess probability. And this thing also is the expression is equivalent to the mathematically it's an equivalent expression to the regular nth order interference terms introduced by Sorkin. And now the final generalization can be seen in terms of asking just the question, why should we treat only bits? Why should these x1 to xm be only bits? Why can't they be something more general? So here I put bits. I don't know if it's a good name for this, but anyways, just a number that goes from 0 to d minus 1, or just sampling from a set with cardinality d. And now we introduce these terms, which are a bit more complicated. So now the probability, Bob is supposed to output this function, which is more or less the sum modulo d. So it's a generalization of the sum modulo 2. However, here we have some weights, some additional numbers, and also this f, which is a mutation, which just physically, operationally corresponds just to relabeling the outputs. So Bob can always just relabel his outputs, and then he will just implement this function. However, here, for simplicity, we will focus only on bits, since this just introduces now unnecessary complications. And in the paper, we show So everything that I will talk about works out also for these games. It's just that now it's easier to talk just about bits. So I will stick now to bits from now on. And now from this game, we have a natural way of, let's say, redefining or extending or reformulating higher order theories. And now we will not label anymore the theories with one integer, so as it was before with, let's say, third order interference theory or something, but we will have a function. Why? Because we have more systems. So we say, so this k will indicate the number of systems or the number of particles, and n of k will be the maximum achievable interference with a restricted number of particles. And here always when I say interference, I don't mean really interference, but this ability to win the game with the boxes, which is not really equivalent to interference in the usual sense. But anyway, so this definition says there exist processes involving k systems that exhibit this n of k order different than 0, but all processes involving k systems exhibit, so you cannot win the game if there are more than n of k boxes. And this is just a random reminder here that n of 1 is then the, let's say, the single system interference again. And up until here, everything was just on the level of probabilities, and I haven't mentioned any physics. So now I will start talking about which theories can exhibit what kind of behaviors in these games. So now first classical theory. We have this that k classical systems cannot collect information about more than k boxes. Here I just mean that if you have, let's say, 5 boxes and you have 4 billiard balls, then you can send each ball through one box, but there will always be at least one box that you will not send anything through it. So it means that in each run, Bob will not get any information about at least one box. And the thing is that parity and modulo are such functions that if you don't know anything about one box, is the same as not knowing anything about all the boxes. So then you're just doing no better than a random guess. So this then means that with classical theory, the classical theory satisfies according to this classification, n of k equals k. So with k balls, k billiard balls, you can win the game with at most k boxes. And here, this is just to say that as in the standard definition, one classical particle constitutes a first order system. We know classical theory is a first order interference theory. Here also we have, again, this first order system. However, 2 classical particles constitute a second order system. Here, just to emphasize that these games are not really equal to interference, because here we see that that here 2 classical particles in some sense interfere, but they don't really interfere. But you can just recover the parity of the boxes using 2 particles. And that's for classical theory. So just n of k equals k. Then next is quantum theory. For single systems. So we know that in the standard, according to the standard definition of interference theories, quantum systems exhibit second order interference at most. And here I will just show a trivial example with, again, just the same thing, that you can win the parity game with 2 boxes using only 1 particle. So it's just the same thing as in the usual. As usually. So here, just for instance, Alice encodes the 2 bits via local phases. So here the 2 boxes are implemented as the local phase shifters, and sends a photon, for instance, in a superposition through the boxes. And it means that the photon is initially in state 1 plus 2, so localized at box 1 or 2. And then they acquire phases which depend on the local input. Phases 0 or pi. And then the Bob can deterministically decode the parity using, for example, a beam splitter, because the state with parity 0 is orthogonal to the state with parity 1. And this is essentially just an interferometer, actually. So yeah. And here I just said that with one quantum system, you can achieve second order. And this extends also to k quantum systems. So with k quantum systems, you can achieve 2k order interference. I mean, here interference again, that you can win the game involving 2k boxes. And one example, just trivial, you can see this by repeating the photon example for each pair of boxes. So for instance, if you have 3 photons and 6 boxes, then you just divide the boxes into 3 pairs and just repeat the same experiment for each pair, and then just sum all the numbers up, and you won the game. However, now this is important that K quantum systems cannot exhibit 2K plus 1th order interference or more. So it means that if you have 3 photons and 7 boxes, then you cannot do any better than just a random guess. And this is then kind of a generalization of the statement that one quantum system cannot do third order interference. Here we have K systems cannot exhibit more than 2K, and yeah. More or less, this follows. I mean, very important in the derivation is that the Hilbert space of composite system is the tensor product of the single system Hilbert spaces, even though the result would also be valid for, let's say, indistinguishable particles, where you would have only a subset of the Hilberts of the tensor product. You just need to have some tensor product structure. And so from this, we conclude that quantum theory satisfies n of k equals 2k, according to the classification. So we saw that classical theory satisfies n of k equals k. Quantum theory satisfies n of k equals 2k. So is it possible to go further to some higher order theories now in GPTs? So we show that under these assumptions, so local tomography and single system operations. By single system operations, I mean that the boxes act independently on all systems. So there are non-entangling gates. Then the order of interference turns out to be additive. So n of k is k times n of 1. So if you have 5 systems of order 3, then the composite system is of order 15, for instance. And this is then a generalization of the classical and quantum theory. And here now just does this statement hold by also if we relax the second assumption, as we do in quantum theory. So in quantum mechanics, I didn't emphasize it before, but it holds for any gates and for any kind of systems, however complicated they are. So I think maybe it could be also, this second assumption could be relaxed. However, this is for future work, perhaps. And now just to recapitulate the story. So we started by treating interference experiments as particular instances of games played by 2 parties, in the sense that if you take this game and restrict the boxes to be implemented by slits, which can be at 0 or 1, if you take the only bits, not bits. And if Alice is sending only a single system or a single particle, and if Bob is putting a screen, then you get, again, the standard interference experiments. So it can be seen as a generalization of interference experiments, and which could perhaps be more apt for information-theoretic considerations. These are just words, but it seems that it could be, because it's a communication task. And then we just introduce this n of k classification. Yes? Okay. Then classical theory satisfies n of k equals k. Quantum theory satisfies n of k equals 2k. And GPTs, we show that local tomography plus single system operations imply, again, the additivity of interference under composition. And now just for the end, I just want to propose an equivalent picture, maybe that can spark off some ideas in someone, I don't know. But just to imagine this scenario not as 2 parties communicating and some boxes in between, but as multiple parties, each of them located at his or her own box. And they are, for instance, they encode locally some information at space-like distances, and then send these systems towards Bob. And then the question is translated into this. So why is there a limit to the amount of global information that Bob can extract? Here by global information, I just mean the parity or model, in the sense that you really need all information. If you don't have any information about one box, it's the same as not having information about anything. So in this sense, I mean global information. So then this can just be seen then as a proposal. So instead of asking why does quantum theory behave in this way in interference experiments, we can ask this question, which explicitly says something about communication and about communication with a finite amount of resources. Also, I think one thing that should be done it would be to maybe quantify the resource in a different way. So maybe not just look at the number of particles or excitations, because maybe it's not really operationally well defined, but to introduce see how these games depend on the entanglement share between these parties located at the different boxes. And this is just a proposal. I mean, for now it's just words, but maybe it can be something. And yeah, that's it. And yeah, thank you for listening. I don't hear. Oh, I don't hear anything.
Hello.
Oh, yeah.
So I think Benoit will arrive to host the question sessions. Perhaps he got disconnected or something.
Okay.
So meanwhile, maybe I can read some for him. Okay, so Stefano Giorgioso was a bit confused by the pictures with boxes. In the two-slit experiments, the slits are usually interpreted as additive subsystems. That means direct sums, while parallel boxes in diagrams usually correspond to multiplicative subsystems, like tensor products. So what's happening here?
I mean, this is not. I should have maybe wrong. This is really, you can just imagine it as a diagram in real space. So you can just imagine that Alice is located here, and there are really boxes in space, and she's just sending something through the boxes. So this is one thing. But also maybe you could imagine these as really being separate systems. Then think about these as acting on the local Fock spaces. But here for now, this picture shouldn't be. I mean, maybe I should have drawn it differently because. But anyway, these are just. You can think one example would be sending one particle in superposition through all the boxes. It can be just that this whole box is acting on one system. These all boxes together are acting on one system. I don't know if I answered. If it's.
Well, I'm not sure because it's not my question, but we'll see.
Yes, and you are invited. You are invited to go in the channel, in the Slack channel, and answer the question in text manner. Sorry, I was disconnected. Cisco and Chrome make my laptop steam, and when it's above 100 degrees, Chrome freezes.
Okay, so I leave you to it then, Benoit.
Okay, so have you asked the other question? So let me ask. So I understand that you asked the question of the first question of Gojoso. I have another one, which is relations n equal k and n equal 2k reminds me of Hardy's axioms. Are you in a way trying to come up with a set of axioms for a GPT in Hardy's axiomatic framework?
I mean, that's not the aim, but I think probably it could be related in some way. I mean, so also because there is connection between higher order interference and these indices, and I'm not sure now which classification of hard they are referring to, but maybe that one about how much how many parameters you need to specify the state, that is related in some way to the order of interference. So then I think it would be also could be connected here, but that's not the aim, and I haven't thought about it. I mean, here the aim is not to find some axioms or something. It's just to reformulate interference experiments and to propose new maybe just new scenarios for looking at limits of quantum theory. And yeah.
And since I'm here, since I have the power of asking the question, I will ask my question and then leave it to you to go to the channel. This will be the last question. So I'm a bit, I'm not sure I completely understood the second order part. How you said that it can only be second order. What could you say again what it means to be second order? Is it
What can be only second order?
yes? Yes, you said. So at the beginning, you said, oh, and anyway, in quantum interferences, you can only go second order and not higher order.
Ah, okay. You mean the very beginning here?
Yes.
Okay.
Yeah.
Yeah. So if you, I mean, that's let's say the motivation here for analyzing these multi-slit experiments is because in quantum mechanics, if you if you send a particle in a superposition through 3 slits, then this thing will always be 0, more or less as a consequence of the Born rule. And then this motivates the whole question of why is it so? So it just follows fundamentally from quantum theory.
Okay. Okay, now I get it. Okay, yes, it's on or off. Okay, perfect. Thanks. So thank you very much. I think we can stop here. I don't know, Matt, if you want to stop the stream or how it works. I will anyway drop off because I need to log into the next meeting. So thank you again, and talk to you on the channel.
Okay. Yeah. Thanks.